Friday at least. That's feels like a big thing for this week. I don't know why. Maybe just because of exams. So I put a couple of homework problems on the free particle due for Monday in class. So if you haven't looked at those yet, that's not surprising, but definitely try your best at them this weekend. And we can talk about them Monday if there's some confusion about those. And then probably the next go round will be all the rest of the chapter 2 problems, which kind of have to do with after we finish our discussion of the finite square well and talk about general kind of scattering problems. So those will be after Monday, but I think I have reading for this weekend to include 2.6. So my goal is just to focus on the Dirac delta function well today, and then Monday talk about the finite square well, but we'll see how far we get with those each day. As you know, I like to do worksheets, and those end up taking more time sometimes. Okay, so we've been talking about several different potentials. We talked about harmonic oscillator and the infinite square well. They only had what we would call bound states, and that means where the probability density for each one of the definite energy states, the solution to the time-independent Schrodinger equation, the probability is sort of localized in space. There's a lump of probability, and then it falls off kind of exponentially, roughly speaking, as you go off to plus or minus infinity. And then we talked about the free particle that had no bound states. All of its states, the probability density kept going on at finite values all the way off to infinity, and that meant that it wasn't normalizable. We're going to start to address more complicated case where we get both bound and scattering states. So let's just talk about, in general, what Griffiths mentions at this point in the book. Classically, what does a bound and a scattering state mean? And then quantum mechanically, there's a little bit of a difference. So just thinking classically, back to classical mechanics, a bound state means that, I'm imagining here's the potential energy. Come on. Having difficulty. Hopefully just startup difficulty. No, that's not working. One more time. Okay, so here's our potential energy function. And if I have a particle moving in that potential energy, it's a classical particle, and I release it at this x value with 0 speed, then all its energy is potential energy, and it changes between that, but it will go between the classical turning points, just bounce back and forth between those turning points. Similarly, what we mean by a scattering state is a state that, so this particle would be bound in kind of a finite region of the x-axis. It couldn't escape to x equals plus infinity or minus infinity. Here's a potential energy function where if I release this particle from rest at this x value, it couldn't get off to x equals plus infinity, but it could get to x equals minus infinity, right? Because it would just keep going and going and going to the left. This particle could get to either side, depending on which way it's going, right? It might get over the top of the bump and keep on going to the right, or it might start going to the left and then keep on going in that direction. Even if the energy of this particle were less than where the peak of the potential energy is, we would still call it a scattering state. We would say, well, if you release it over here, it'll keep going in that direction. If you release it over here, it'll keep going in that direction. So scattering state just means you're not bound in a finite region of the space that you're sitting in. And here we're just thinking again in one dimension. Okay, if you can get either to, in one dimension, if you can get to plus or minus infinity, you're called a scattering state. Here is the interesting case for quantum mechanics where we've got something that kind of looks like, well, it essentially is this potential, but we're going to lower the energy down so that classically a particle would be confined in this region. But quantum mechanically, we'll find that if something has a certain energy, or at least a linear combination of energies, and you start it in this region, if the energy looks like this, then it will leak out into the through the classically forbidden region into another classically allowed region. Okay, so quantum mechanically, we would still call potentials that look like this. In other words, potentials that keep going up and up and up and up as you go to plus infinity or minus infinity, like the infinite square well or like the harmonic oscillator. The states associated with it would be bound states. Similarly, if you have potential energy where the energy of the particle is such that asymptotically, if you go to one side or the other, or both, doesn't really matter, if asymptotically the energy of the particle is greater than the asymptotic value of the potential energy, then we call that a scattering state. So quantum mechanically, that sort of agrees with the classical case. This case is different here. We would call, if we had a potential energy function that looks like this and a solution to the time-independent Schrodinger equation that has this energy, we would call that a scattering state, because we're going to find out that the wave function isn't confined just to this region. It actually keeps on having a non-zero amplitude all the way out to infinity. So it won't be normalizable. And that phenomenon is called scattering. And let's just, tunneling. And let's look at an example of that. I thought I had this open here, but, well, let's click it again. Oh, I see it opened in Edge. There we go. Okay. So let's close that one out. Here's a potential energy function shown by the continuous white curve at the top. Oops, I didn't want to do that. Let's click up here. Potential energy function is given by this white curve up here. So it's got a high potential energy on the side and then a lower potential energy, maybe zero for a while. But then there's a barrier in the middle where the potential energy goes up and comes down again. And then there's another region where the potential energy is low, and then it goes high again at the end. And so if I consider a definite energy state that is less than the height of the potential energy function, well, there's no way to talk about tunneling there, because as we know, the probability density is independent of time. We're talking about definite energy states. So we're never going to see probability leak out. That would mean the probability density is a function of time. And if you're talking about a definite energy state, it is never a function of time. But what I can do is I can put a fairly wide initial state. Let's call this initial state. I'm going to put most of my probability on the right-hand side of the well and watch what happens as time goes on. So as time goes on, we let this evolve. We're seeing the probabilities staying mostly on the right-hand side. But very gradually, it starts to leak into the left-hand side. And if I increase the simulation speed, we'll see that, it sort of freely gets back and forth. Now, it's possible that this state, it's not an energy eigenstate, because its probability density is not independent of time. So it probably has some admixture of energies that are above the maximum of that potential barrier in the middle. But we could form a state that's not an energy eigenstate. So let me clear this out. I'm going to put it in, say, the ground state for this well, and then I'm going to add a little bit of the first excited state into it. So it's a linear combination of the ground and first excited state. Okay, let's unstop it now, and I'm going to turn the simulation speed down. Oh, that wasn't too good. There we go. So I've chosen a linear combination of the ground and first excited state, and you'll see those energies are down here. It's a linear combination of two energies that are way below the maximum of the potential barrier in the middle of the well. And those are the only two non-zero amplitudes. And right now it's shouldn't be stopped, so it's moving forward in time, but I'm going to increase the simulation speed, and you'll see as time goes on, that probability is able to sneak back and forth from one side to the other, even though the energy of the two states it's composed of is way less than the barrier of the potential, the potential barrier in the middle. So it can sneak between no matter what, even if the energies involved are really below where the barrier is. So that's tunneling. You don't see tunneling in a definite energy state because the probability density never changes with time. But if you take an admixture of very low energies, you can still see the probability density slosh eventually through the well. Okay, let's go back to now the slides. So because of tunneling, what we're interested in is how the energy of, if we're talking about a definite energy state, whether or not it's a scattering state or a bound state just depends on asymptotically whether the energy of that state is bigger than the potential as x goes to plus or minus infinity. So a bound state is going to be any allowed energy state such that as you asymptotically go to minus infinity or asymptotically go to plus infinity, both of these are true. In other words, the energy is asymptotically less than the potential energy on both sides. That's sort of like the infinite square well, because the potential energy goes to infinity. But it doesn't have to go to infinity. It could also, if I graph the potential energy as a function of position, it could just go down for a while. And I might find that there's a bound state with this energy. It would be bound because asymptotically the energy of the state is less than the potential energy there. And we'll see that for the finite square well in section 6. In contrast, a quantum scattering state is one that is asymptotically greater than the potential energy. The energy of that state is greater than the potential energy on either side or both. Doesn't matter. We'll call it a scattering state if it can get out, kind of classically speaking, to plus or minus infinity. Okay, so where we're heading with this is that so far we've seen two potential energy functions that only had bound stationary states or definite energy states. The infinite square well and the harmonic oscillator, there was an infinite collection and they were all bound states. The probability density went very rapidly to zero once you passed a certain position. And the free particle only had scattering states, right? Those were those e to the ikx kind of states, and they never fell off to zero, right? They just kept their large amplitude. And that means the energy, which had to be bigger than zero, was larger than the asymptotic value of the potential energy, which was zero in that case. We assumed the potential energy was zero. Okay, our next example is going to be interesting because it's the first one that includes both bound states and scattering states in one potential. And as you maybe know from the discussion of the hydrogen state, the hydrogen wave functions, it has both bound states and scattering states in its spectrum. So this is kind of the more typical case that you're going to have some bound states and some scattering states. Okay, so back to what we were doing. We're going to solve the time-independent Schrodinger equation with this potential. The potential is zero everywhere except where this delta function has its spike. It has a spike at x equals 0. Remember, delta of x minus x0 has a spike at x equals 0, x equals x0. Here, this has a spike at x equals 0. Delta by itself has an area 1 under it, so that means alpha times delta has an area alpha under the curve, and putting the minus sign in front of it means that instead of the spike going up, it goes down. Okay, so, well, maybe I'll draw a picture in just a second, but we want to solve the time-independent Schrodinger equation with that, and there were a couple reading response questions. about delta functions. So let's just review a little bit, because for some of you, this is the first time encountering that concept. I still don't understand how we can integrate a delta function if the function is infinitely narrow and infinitely tall. So you can think of a delta function as just a narrow function that has area 1 under it. And it's so narrow that you kind of just don't notice the details there. We don't really care. It's so narrow, we don't care if it has a square top on it, or it's actually really Gaussian shape, or it's like a sine of x over x kind of function where everything is compressed really close to the center. But we can integrate it because we're thinking of that delta function as being, you know, just like you could imagine in physics 110, where people are some people are encountering instantaneous velocity and acceleration for the first time. And you could think of instantaneous velocity as just average velocity, like delta x over delta t, over a very small time scale. Yeah, I know technically we should let delta t go to 0, but it's, you know, you get a very good approximation to your instantaneous velocity when you're driving a car if you take delta t of 1 millisecond or something like that, right? So it's the same way here. I'm going to think of delta of x as being, or delta of x minus x0, as being a very narrow function. So narrow that I probably won't notice it experimentally. But it still has a definite structure, and the area under it is 1 if we're talking about delta of x minus x0. Okay, and that means that if I multiply by a positive constant alpha, then the area, you know, since I integrate this and it has area 1, if I integrate this function from minus infinity to infinity, I'm going to get alpha under the curve instead of just 1, right? Because the alpha would just come out of the integral, and then I'd have an integral of a delta. Okay, let's see, share screen. What defines a particle as having a delta function? I don't know, I wouldn't define a particle as having a delta function. Here we're considering a potential energy function that just in words is a very narrow but possibly very deep potential energy well. So think of it as something that at a certain location is suddenly going to go down really deep and then just as suddenly come back up again. You know, there is a sense in which a particle could have a delta function or be a delta function if you think of it as a function of x at some particular time. Psi is very, very localized. That could be my initial condition, and I could say it's very close to a delta function at time t equals 0. Where does the fact that a delta function multiplied by an ordinary function is the ordinary function evaluated at the center of the delta function come from? So we talked about this back when I introduced delta functions, but it's worth thinking about again or reminding ourselves because we're going to use this property. If I integrate from minus infinity to infinity of a delta function with its spike at x0 times any continuous function with respect to x, and I don't even have to integrate from minus infinity to infinity. I could integrate from a little bit less than the location of the spike to a little bit greater than it, and I don't miss anything because the delta function is 0 everywhere else, right? When I do that, the claim is we just take the other function and evaluate at where the spike is. That's the claim that's being made here. And the justification is what? Well, when I write it this way, notice if f is a continuous function, if we're integrating just over a narrow region that includes x0, f doesn't have any chance to change far away from x0. So this, in this narrow range of integration, this is approximately f at x0, right? Because if f is a continuous function and I'm integrating over a microscopic region of the x-axis, it's going to be it's going to stay close to its value at x0. And then I can pull that out in front. What's left is an integral with area 1 under it. So this is multiplied by 1. That's where it comes from, but good fact to remember. Okay. Anyways, here's our potential energy function. And so we're thinking of it as something that here is 0. If I'm graphing the potential energy, this one has a very deep well in it, that has area minus alpha, negative area in the math sense, if I graphed v of x as a function of x. Okay. And we want to solve the time-independent Schrodinger equation for solutions. There it is. I've just plugged in the potential energy function minus alpha delta of x into our usual equation. And because we're going to have both bound and scattering states, we'll see that things go differently if we assume E is less than 0 or E is greater than 0. Notice, if E is greater than 0 here, we're talking about a scattering state. If this is the energy we're finding, if E is greater than 0, that means the energy is asymptotically greater than the potential energy. So we're talking about a scattering state. Whereas if we find an energy, of course, we already talked about that problem where the energy's got to be bigger than the minimum of the potential energy. This one actually goes down to minus infinity, so we don't have to worry about that too much. But in this case, the energy is asymptotically less than the value of the potential energy, so that will correspond to a bound states. So we're going to try to find the bound states. That's a little bit more familiar to us first. And in this case, because, this is actually infinitely thin at the origin, there's really only 2 regions that we need to solve this in, and it's really easy to solve it there, x less than 0 and x greater than 0. And then we need to worry about, so if we get separate solutions in those 2 regions, then we need to apply boundary conditions to connect those 2 regions, right? Something strange is going on at the origin, so we'll have to apply the boundary condition. Okay, so when x is less than 0, hey, it's just like solving the free particle, right? There, v is 0. If x is less than 0, v of x is 0, right? The delta function's only at the origin. So same kind of thing happens, except we got to remember we're talking about bound states here. We'll deal with the scattering states later. Bound states are where E is less than 0 down here. So I've got to remember that symbol E, I'm assuming for the time being, is less than 0. That means minus E is greater than 0. So this big combination of constants that's sitting out in front of psi in the time-independent Schrodinger equation is positive because E itself is negative, right? So the minus sign makes it positive. And therefore, I'm going to define the square root of all this mess that's sitting in front of psi to be a constant, and we'll call that constant kappa. I can't remember if Griffiths calls it kappa or some sort of script k or whatever, but it's not the lowercase k because it's got that minus sign under the square root, which looks a little bit weird, but you got to remember E is negative 2, so there's really no minus signs under the square root for that definition of kappa. Okay, and then we've got a nice familiar differential equation. D squared psi dx squared is a positive constant kappa squared times psi. The solution to that, as you can get from by inspection, is a linear combination of, decaying and increasing exponentials. These things are supposed to be kappas up there. It's a little bit hard to read there, but they're not k's, they're kappas, right? So exponential growth and decay. If you're not familiar with that, just plug it into the differential equation. You'll see both of those are 2 linearly independent solutions, and so that's got to be the most general solution. So here's the most general solution for x less than 0. Now, we want it to be normalizable. So if we're talking about x less than 0 and we have a decaying exponential function, right? If we have some part of our wave function that we're looking at, our time-independent Schrodinger equation, that's a decaying exponential that's doing this, and it's supposed to have that form for x less than 0, we've got a problem over here. It's not normalizable. Whereas an increasing exponential function has a perfectly finite area over there. We're only finding the solution for x less than 0. So when x is less than 0, the coefficient of the decaying exponential has to be 0 just to make it normalizable. because we're just doing x less than 0. And of course, a very, very similar thing happens for x greater than 0. For x greater than 0, we can only have the decaying exponential 1. We can't have an increasing exponential if we're in a region where x can get arbitrarily large. Okay, so our basic solution has, for x less than 0, it's e to the kappa x. For x greater than 0, it's e to the minus kappa x. Now we got to apply our boundary conditions that has to be true. We had two regions. Let's connect them up. The first boundary condition that's always true, at least for the potentials we decided to limit ourselves to, is that psi has to be continuous across boundaries. And requiring that those two solutions are continuous is the same as you could just plug in x equals 0 on the left-hand side, x equals 0 on the right-hand side. You'll find the coefficients have to be equal. And therefore, I just changed my f to a b there. In other words, we had something that looked like, if we kept those coefficients not equal, we'd have solutions that looked like this, and maybe the other one would be like that over there. And if the coefficients out in front aren't equal, these two wouldn't match up. So if we want them to match up, they've got to have the same coefficient out in front. But you could just do the algebra and show yourself easily in one step that that has to be true. Okay, so that's we're just whittling down each step, simplifying what psi has to be. Now, there's sometimes a second condition, and that is the continuity of the derivative, which we said only technically applies when v doesn't go to infinity at any point. But here v is going to minus infinity at x equals 0. So we don't expect necessarily psi prime to be continuous. And in fact, we'll see that it's not. It's going to have a kink in it, just like this function that I've got here. But the question we still want to answer is how big of a kink, right? I might have a very shallow kink, or I might have, a really sharp kink in the middle. And we're going to find out that there's a different condition that allows us to put restrictions on what this kappa can be there. And here's what Griffiths shows, and we can do it here on the board. What we're going to do is we know the conditions, these two conditions, continuity of psi and d psi dx, came from inspecting the time-independent Schrodinger equation. So what we're going to do is actually, instead of just taking the Schrodinger equation by itself, time-independent Schrodinger equation, let's integrate both sides of the time-independent Schrodinger equation. So here it is right here. Let me go to the board and write this down, because I think some people asked about it in the reading responses too, and it's a good, I can't remember how much detail Griffiths goes into, but you definitely have to work out the details to figure out what he's talking about. So if I go back to here just so I can see it, time-independent Schrodinger equation, let me just solve for d squared psi dx squared. Okay, so here's our time-independent Schrodinger equation, d squared psi dx squared, and let's put everything else on the other side. The alpha delta has a minus sign when it's on the left-hand side. It would get a plus sign when I move it to the right-hand side, but then I'm going to move over the minus sign from the other constants that are out in front too. So I think you can tell me if I'm wrong. This is equal to 2m alpha, and it still has a minus sign out in front of it. 2m alpha over h bar squared times delta of x times psi minus 2me over h bar squared psi, right? And those psi's are functions of x. Okay, so Griffiths is saying, this is just the time-independent Schrodinger equation for our potential. I happen to solve it for this. And now let's integrate from x equals minus epsilon to plus epsilon. We're imagining we're going to let epsilon go to 0. dx. if we do it on the left-hand side, we got to do it on the right-hand side. This doesn't have any x's on it, so I can just put this here, minus epsilon to epsilon dx. Sorry, I'm sort of squeezing things in here. And here's a minus epsilon to epsilon dx. And now we got to think about all of those. If I let epsilon get really small, what is this last integral here, the one on the very right, going to get very close to as epsilon gets really, really close to 0? It's going to get close to 0 because any normal function, when you integrate it over, that's not true for a delta function, but any normal kind of continuous function, and we already said psi is continuous, when you integrate it over a tiny region that gets smaller and smaller, there's 0 area left under the curve, right? So this is going to go to 0 when I do that integral. What about this integral here, the integral of delta of x times psi of x, for our nice continuous psi? Psi at 0, right. That's our property of the delta function where we say, where's the spike of this? At x equals 0. So when I do this integral, as long as the domain of integration includes that spike, we just evaluate this function at the x value where the spike is. This thing right here, well, I've got an integral of a derivative, right? I can think of that as the integral of the derivative of d psi dx. Second derivative, but that's the derivative of d psi dx. And we can use the fundamental theorem of calculus. When you have the integral of a derivative, that's equal to the function itself evaluated between the two limits. So this integral right here is using the fundamental theorem of calculus. I'll just put FTC, fundamental theorem of calculus. That's equal to the thing that we were taking the derivative of under here, and this is a derivative of d psi dx, evaluated between the upper limit and the lower limit. And I can kind of think of that as epsilon goes to 0. This is d psi dx evaluated at 0, just above 0, right? Sometimes in math classes you write 0 plus, right? Minus d psi dx on the other side of 0, the negative side of 0. Okay, so that's saying this change is related to minus 2m alpha over h bar squared psi of 0. Let's see if does that take us to where I wanted to go on the slides? I can't remember. Yes, there it is. So that's what we just found out. The change in d psi dx from one side to the other side of 0 is equal to this. And now let's plug in what psi of 0 is. Does anybody remember from the slides before? When we plug in x equals 0, we already made it continuous. What value does psi have right at x equals 0 where that cusp is? It's b for the constant we had, right? Because we had b e to the plus kappa x, b e to the minus kappa x, but those exponentials go to 0 at x equals 0. So this is equal to b. Let's see. Okay, right-hand side, we have a minus 2m alpha over h bar squared times b, because psi of 0 is b. On the left-hand side, I've got to think about this, right? Remember, our function looks like b e to the kappa x and b e to the minus kappa x when x is less than 0 and when x is greater than 0. So let's take that derivative. D psi dx on the positive side, here's the positive side, is minus kappa b times e to the minus kappa x, and we're going to evaluate that at x equals 0, so the exponential goes away. So I think if you think about this, you'll see this is minus kappa b, this one right here, minus d psi dx when x is less than 0, evaluated at 0, and that's going to give me a kappa b times something that goes to 0. Okay, so I've got minus signs on both sides. This is minus 2 kappa b. Let's cancel the minus 2's. And let's cancel the b's. I've got a b on both sides too, right? And we can also cancel the minus 2's. And that will give me kappa is equal to minus 2m alpha over h bar squared. Okay, and now going back to our argument earlier, let's just flip back a couple slides. Remember, kappa, just like, usually when we say k's, kappa is just a placeholder, right? It's something, shorthand for something that depends on energy. So this is saying, look here, we've only found alpha is a particular value, h bar is a particular value, m is a particular value for our particular particle that we're talking about. So this is one value on the right-hand side. We found one kappa, and that means there's one associated energy. We were looking for bound states. We found only one allowed kappa, and that means there's only one allowed bound state, and here we can calculate its energy. If you invert the formula shown right here, oops, sorry about that. If you invert this formula for E, solve it for E, you'll just see E is equal to minus kappa squared, h bar squared, kappa squared over 2m. Remember, we're expecting negative energies, right? Because we're looking for bound state, so it's got to be below the asymptotic value of the potential. Okay, so let's fast forward to where I was. Where is that? Okay, so here's the only one allowed value of kappa, and translating it to energies, the energy is related to kappa this way, and therefore there's only one allowed energy, which is minus m alpha squared over 2 h bar. So one bound state. Okay, and it looks like exponential increasing and decreasing functions that meet in the middle with a kink or kind of a cusp shape. All right, and I guess I should fast forward here, but you can normalize it, of course, because those exponential functions have finite areas under them on the left-hand side and the right-hand side. Instead of having a multi-part function, I can just write it as e to the minus m alpha absolute value of x. That includes what's happening on x greater than 0 and x less than 0. And you can integrate from minus infinity to infinity and see what constant you need out in front to normalize it. There it is. So here's our one bound state, and here's our one bound energy. Questions on that part? So our bound state, again, just to give the intuition about it, we're talking about to draw a diagram in the way that Griffiths might draw it. Here's on the same diagram, he likes to draw the potential energy, which I'm going to draw, sort of like that. And we found one energy here. I might call that E bound. I don't have the formula in my head right now. And its associated wave function starts off, very close to 0 and goes up like an increasing exponential and then goes down like a decreasing exponential. So that's the shape of the one bound state. Okay, so any questions before we try a worksheet? So our spectrum has only one bound state. We're gonna find there are unbound states as well, but let's try this problem. Here is, again, one of my favorite randomly not so randomly chosen initial states where psi is constant between A and 2A and 0 everywhere else. And I've bothered to normalize it for you. And what I want to do is find the probability that if we measure the energy of the particle in this state, so we're saying, oh, I'm not in this state. My state looks like this. Here's A, here's 2A. My state goes up to a constant and then back down to 0. That's going to be a linear combination of a lot of different energy states. It's clearly not just this one, right? But this is going to be part of the ingredient that's required to go into this. There's also going to be a lot of scattering states that I would need, and we haven't even talked about those yet. But if we're in this state at some particular time and I measure the energy, I want to find the probability that I get this bound state energy. And that means, as you know, again, we didn't prove this, we're going to postulate it in chapter 3. The thing that corresponds to that probability is whatever the coefficient is in front of that bound state, magnitude squared is the probability, right? We said the Cn squared is the probability of measuring En. So whatever the coefficient is in front of the bound state, that's the magnitude squared of it is going to be the probability we're talking about here. So if we start out in this kind of state, there's a certain probability that when you measure energy, you'll find the bound state energy. And the formula for the bound state C is the same formula we had before. Somebody help me write it down. How do I find all of the C's always? What do we do? Psi at x and 0 times psi bound, which is that formula we just found, right? And integrate from minus infinity to infinity. We're always going to do that. And in fact, we do the same thing even if this is an unbound state, a scattering state, right? We said it has the exact same formula. So try doing that calculation. And the formulae you need are on the slide there. This should technically have a star on it, but again, in this case, it's a real function, so the star doesn't come to anything. But that's not always going to be true. So I don't think it's as simple as that. There's no delta functions in there, right? Because psi at x0 is this function. And our psi bound is this function. It's not a delta function. It's that one that has a exponential kind of function on both sides with the kink in the middle. Yeah. Well, you're never going to have the infinity and minus infinity limits because this function is only non-zero between a and 2a. So you change your limits to a and 2a. And then in that region, x is positive. So you can just throw away the absolute value signs and just do a normal exponential integral. Okay, let's try to do this together. So again, we said that the C corresponding to the bound state energy, I'm just calling that C bound, is the integral from minus infinity to infinity of psi at x and 0 times this bound state time independent Schrodinger equation function starred, right? And for us, psi of x0 is only non-zero between a and 2a, so I can reduce the integration bounds from a to 2a. In that region, psi of x and 0 is 1 over root a. Okay. And then I just copy down what psi bound is. The star doesn't really matter. So the normalization constant looks like this. And then we have an e to the minus m alpha absolute value of x over h bar squared. And I've got to integrate with respect to x. And that's easy. That's just a normal exponential function because between a and 2a, x is positive all the way between a and 2a. And therefore, I can throw away the absolute value signs there, right? I don't need them if we're only in the positive x region. And that's an integral I can do. I guess the square root of alphas cancel between here and here. And so I get a square root of m over h bar. Anti-differentiate this, and I'll get a factor of minus h bar squared over m alpha times e to the minus m alpha x over h bar squared evaluated between a and 2a. I won't carry it any farther. You just substitute those in. We get some expression that depends on a bunch of constants, but that's fine. And then we take the magnitude squared of that to get the probability that was asked for. Say that again. You're right. I canceled an A against an alpha. Okay. So this should be an alpha there. And there should be maybe square root of m alpha over A times a 1 over h bar, I guess. And we can cancel more stuff there, but. Okay, B is no more or less difficult. You're not asked to do the integral because we can't use our Gaussian integral tables, but I just, just as another example, you might try writing down the integral for what is C bound for this traveling Gaussian state. So this is the one where we have the initial state is some Gaussian envelope with the wiggle underneath it. And as time goes on, the envelope kind of flattened and it kept moving on. What we were talking about with group velocity and phase velocity. And we're going to put it next to this psi bound and integrate. And you can't do the integral. in this case, even with our tables, we can't do the integral, but that's how you would do it. You could do it numerically if you knew what all those constants were. Any other questions on those? Okay, so not so exciting because we only found one bound state, but hey, that's kind of interesting. Everything else must be scattering states. And of course, there are a lot of scattering states. There's a continuum of scattering states, and here's how we find them. If we're talking about scattering states, now the energy has to be asymptotically greater than the potential, so we're talking about positive E's, right? We're going to assume this E is positive, and therefore this thing in the time-independent Schrodinger equation that's in front of the psi is truly negative. So accepting the minus sign, the stuff out in front is positive, and we're going to call that k squared, just like we have before for the free particle. So this is our usual old definition of k that we've used before. For the free particle, that's the harmonic oscillator differential equation, and it can be written as linear combinations of cosines and sines of kx, but you know we like to write it in most cases when we're talking about scattering states, you'll see why in just a second, as a linear combination instead of those corkscrew shaped traveling complex exponential kind of wave things. Okay, so when we do that in the region where x is positive and x is negative, it's going to be a linear combination of those two kinds of functions in the two regions. I just put arbitrary constants in front of all those, but the k is going to be the same for x less than 0 and x greater than 0 because we're talking about the same E and V is 0 there. So there's only one k in that region. Now this looks complicated because A, it's not normalizable. These are functions that never get any smaller as you go off to plus or minus infinity. And we've got 4 undetermined constants in there. But as you know from the reading, that we have to sort of think about this for a little while. But let's first think about these functions. What do they represent? If we put in the time dependence, right, and watch these functions do whatever they do as a function of time, e to the ikx versus e to the minus ikx. This is a voting question having to do with that. Let's just consider the e to the plus ikx one. It represents a wave. Which way is it traveling? Left means negative x direction, right means positive x direction. It's unclear because it depends on when we put in the time-dependent part. That could make it travel in either direction or none of the above because it's not going to be like a traveling wave at all. Okay, let's see a vote. It's between the B's and C's here. It's either traveling to the right or it depends on the energy part. Let's just write it down, right? I say, if this is one of my definite energy solutions, e to the ikx, and sorry, let me just... What's that? Change your answer, okay. So we know how to make it time dependent. We put in e to the minus I et over h bar, and now E, it's the usual relationship between K and E, right? So this is going to be, well, it doesn't really matter. E is positive, that's all that really matters here, right? So we have, let's combine these together. This is E to the I, I, K, X, minus E over h bar times t. K is positive and E over h bar is positive. So the question is, does this travel in the positive or negative x direction? And, you know, to be at a particular point on the corkscrew, that means this thing in parentheses has to have the same value. So as t gets bigger, that point on the corkscrew has to get bigger, move to a bigger location too, in order to keep the phase of this constant. So this will move to the right. As time gets bigger, x has to get bigger too to stay at the same point on the corkscrew. So this travels to the right or in the plus x direction. And that means just by looking at this as a solution to the time-independent Schrodinger equation, I know this is traveling in the plus x direction. And just by looking at this similarly, that would change this to a minus sign there. That travels in the minus x direction. So I can look at those solutions and they do correspond to traveling waves even before I put in the time dependence. I can see that. Any questions on that? So it, you know, you just have to add in the time dependence and see how it shakes out there, but that's what happens. Okay, so when we're looking at this, this is a complex exponential traveling wave that travels in the plus x direction. This corresponds to a wave traveling in the minus x direction. That's not immediately obvious when you look at those. Once you know what happens as a function of x, you automatically know how the time dependence has to go, and it can only go one way because there's only one factor we put in to add the time dependence to those. Okay, so I know what those correspond to. We still have two regions, right? There's x less than 0, x greater than 0. We got to apply continuity at x equals 0. And when we do that, that's pretty easy to do. I just substitute in x equals 0 to all of these and require that this equals this. That's just a plus b equals f plus g. Not my, you know, it's easy relation. It's not clear what it means yet, but let's just hold on to it. I just half boxed it there. Again, the derivative is not continuous, but we can replace it with the relationship that we derived before, right? The discontinuity in d psi dx has to be equal to this. So let's apply that to this. Same reasoning that we had for the bound states. And when we do that, you just have to kind of evaluate psi at 0, and all these x's are going to go to 1, so that gives you the right-hand side. And I have to take the derivatives of these and then evaluate at x equals 0 on the left-hand and the right-hand side. This is how it shakes out over here. Blah, it's kind of ugly, but so I've got two constraints on those four constants. And at this point, Griffiths, well, I have 1 minute left. We have two equations for four unknowns. That still doesn't seem really hopeful. We were kind of hoping for at least 3 or 4, right? I would like in principle to say, I don't want any unknown constants out in front. Unfortunately, we're going to be stuck with one of them because these are not normalizable functions. So I can't use normalization to determine one of those constants, but we've got constraints on 2 of them. And now Griffiths says, you know, let's think about the meaning of these constants. This is a wave traveling to the right in the in the positive x direction. This is a wave traveling to the left in the positive x direction, and similarly for the negative x direction. Let me not ask that there. So he says, in a typical scattering experiment, we might say the beam is coming in only from one direction. So I'm shooting these particles towards a target. My target is represented by this simple delta function kind of potential, right? We're shooting a beam towards it. It should only be arriving towards the delta function potential from one direction. It depends on which direction the beam is coming from. So Griffith says, you know, let's assume the beam is coming from the left. That means I shouldn't see any wave traveling in the negative x direction in the positive x region, because there's no beam that's shooting towards the origin from that side. So we're going to say, this is the interpretation of all these, the amplitude of 4 different kinds of waves. We don't want a wave in the x greater than 0 direction that's heading towards the origin. This is the one that's heading towards the origin here, right? For x greater than 0. Am I agreeing with this? Yes, if it's coming in from the left, something is wrong with this. If it's coming in from the left, there shouldn't be a beam coming in the negative x direction from the right. And that means mine may disagree with how Griffiths has parameterized this. But in the region to the right, that's x greater than 0, we shouldn't see a beam traveling to the left because that would be a beam heading towards the origin from plus infinity. And that would mean B is 0 in this case. Let me check, since we're out of time, for next time and see if I'm disagreeing with Griffiths. He may have the beam coming in from the right and somehow I mixed it up here, but it looks like that shouldn't correspond to G equals 0. Rather, it should correspond to B equals 0. We don't have any beam coming towards the origin from the right-hand side, but I'll check that before next time. So we're going to use that to get rid of yet one more constant, and then we'll have only one undetermined constant there. All right. Thank you. If you have any questions, you're welcome to hang out for a little bit, but have a great weekend. Try those homework problems, and we will definitely start getting into section 2.6 on Monday after we finish talking about these scattering states. So read 2.6 before Monday at 8 a.m. and have a wonderful weekend.
You too.